Hi, so today we've got this to take a look at. This was sent in quite a few months ago. I'm afraid I can't find the original email to find the name, but thanks anyway. It's someone from a recycling company. And this is a scanner for dental x-ray phosphor plates. Now when I first got it, I was really busy, so I just sort of put it to one side and I thought it was maybe just an optical scanner for like film x-rays, but it's not. It's a phosphor type system, which is a sort of intermediate between the old film type x-rays and fully digital x-ray systems, whereby the plate, which is actually illuminated with the x-rays, has got a special phosphor on it, which produces a latent image. Then gets developed by this unit by scanning it with a particular wavelength of laser and then looking at the light that it gives out, and that depends on how much x-rays it received during the exposure time. So you've got the advantage over conventional x-rays in that it's very, very quick developing. You don't have to wait to develop the film, you don't have all the chemicals. It's not quite as quick as digital x-rays, but in principle it's cheaper because the phosphor plate is just a plate with a material on it. I found one online price for this at about 6,000, so it's not a cheap piece of kit, and clearly not just a simple scanner. It's got quite a lot of weight to it for very nice high quality mouldings. Doesn't do a great deal when you turn it on. It's got an Ethernet interface. There's a few sort of configuration things here, but on a very sluggish touchscreen, but there isn't anything particularly interesting in this menu. I can make a few noises if I just sort of stick some something in the top to emulate the cartridge. So erasure, I think that's my guess, is that when you scan it, it actually scans it and then erases the image. This is probably just a facility for it erasing, just erasing. Yeah, so it thinks I've put something in there. It's making various whirring noises, and it's probably going to complain that it hasn't actually seen the real thing. Obviously it needs to have something that's actually the right physical size in there. So stripping all the covers off, it's made of this sort of, we've got lots of these sort of very high quality plastic mouldings, as you sort of expect for this medically type things. It's probably quite a significant part of the cost. Obviously you want medical things to look nice and shiny and professional. And we've got a standard TFT display, a little board on the back which has got a backlight supply and some filtering. There's these ferrite cores over the ribbon for EMC filtering. Quite a few boards in here. There's one down here which has got the connectors on it and some power supply stuff. There's a USB micro B connector on there. It's not actually externally accessible directly, it's sort of underneath that plastic cover, so I'm guessing that's probably for something like firmware recovery or some sort of peripheral or something, but that's not normally accessible in the product. A very chunky base. I think it's just like a big solid metal base just to give it some weight to make it sit nicely and again give it a bit of a quality feel. The main chassis is fairly sort of quite thick steel, maybe for optical, mechanical stability for the optics. One thing I noticed on this board here is some high voltage symbols and some very big capacitors, so that makes me think maybe there's a photo multiplier in here for doing the optical detection. There's a top PCB here, there's a big NXP processor, Ethernet transformer. Background here there's a small RF connector. I originally thought that was Wi-Fi, but actually I think that's, if there's a photo multiplier, that's probably the output from the photo multiplier on this. Feels like sort of Teflon cable, so that's like a high impedance, high sensitivity input, so that'll be why they're using coax for it. There's a stepper motor here with, for some reason they've used two belts. That goes through here. There's looks like a worm drive driving something. I'm guessing that's probably the actual drive that drives the plate through the device. Some sort of high quality ball bearing mounts on there, so it's sort of clearly built up to a spec instead of down to a price. Now I powered this up with the lid off, mainly to try and find some serial debug outputs, and it produced a few error messages, and this probably gives a bit of clue as to what's in here. There's obviously door detection, sort of photo sensors, well, door motor, door current, so there's a door that sort of opens and closes when the thing drops in, so it's probably current sensing that to detect jams. Real-time clock, FPGA, room finding system, Ethernet. So the various LEDs, Also FPGA laser, FPGA MEMS, which sort of implies there's maybe some sort of accelerometer in there. Not quite sure why there would be that in there, unless maybe that's for something else. A few other things, so sort of just error messages can sometimes give a bit of a clue as to what's inside the box. So with this plastic cover off, there's just got this little gate for letting the plate drop through. There's a NXP LPC 4350 processor, external flash, serial flash for the firmware, Altera Cyclone FPGA, Ethernet controller, various bits of RAM, analog front end for the photo multiplier, a little bit of power supply stuff there, various other odd bits and pieces. Not much on the back, some power supply stuff, step motor driver, again some optical sensing for the plate sliding through here. Nothing much else of interest on that side. And now this is off, we can actually see the rollers that take the plate in. So if we turn the step motor, this turns around very slowly, so I'm guessing this goes through very slowly to get a high resolution scan. Now, I can't find a figure on the image resolution, but it says about 20 lines per millimetre. Also, while I was looking through the manual, I found that the reason for these removable parts is so that these can be sterilised, because these parts come into contact with the plates. So there's the option to remove these so they can go through sterilisation procedures. So you can see this is the stepper motor that moves the plate through. There's also a geared DC motor that operates a cam, which opens and closes the shutter to allow a new plate to drop through, and then closes it back again. That's probably partly down to light proofing as well, so there's no light enters when the thing's actually being scanned. And it looks like this board is a dedicated high voltage power supply for the photo multiplier. It's just got sort of power in with sort of quite a lot of filtering from the input board. It also says LM HV, so presumably high voltage supply. Couple of driver transistors, and then on the back there's a transformer that looks very much like a CCFL type transformer, so that's producing something, I'm guessing, of the order of high hundreds to low thousands of volts at a very low current, probably a few hundred microamps at most. And on the end there, this roller, this board here with some sort of device. I'm guessing that's probably doing some sort of feedback. It's some sort of rotary encoder, I'd guess. Let's take that off and take a look. And on the back of this high voltage board, also we've got a divider, so obviously a string of series resistors to balance the voltage across each of them. Linear Tech switch mode controller there, so that's all fairly straightforward. And this is the power board that goes at the bottom. Nothing particularly interesting here. Ethernet connector, power in, USB, little sounder, and just various connectors. A battery for the real-time clock. Sorry, a super cap for the real-time clock. And a few just bits of power supply stuff. And this encoder for the roller is a AMS AS5048, which is a 14-bit magnetic rotary position sensor. If we use this magnetic field viewing film, we can see that there's a sort of sharp line field. So that's on this magnet on the end of the shaft. That's producing a sort of sharp magnetic field transition that's then sensed by this magnetic sensor to detect the position of the feed roller. So removing this plastic cover, we start seeing some optical goodness in here. There's the base of the photo multiplier down there, some lenses, there's a laser here, and what I think is like a voice coil mirror just down there. There's sort of mirror in a coil, so that's probably what produces the XY scanning. And a couple of lenses too, and then there's a mirror down here that deflects that 90 degrees to go downwards onto the plate. So this is the laser assembly. We've got a laser diode here, beam comes out here, bounces off there and onto this little mirror, and there's a couple of little magnets on the back, so these coils produce the XY scanning across the plate. And this encoder for the roller is a AMS AS5048, which is a 14-bit magnetic rotary position sensor. And if we use this magnetic film at. If we use this magnetic field viewing film, we can see that there's a you can see the sort of sharp line field. So that's on this magnet on the end of the shaft. That's producing a sort of sharp magnetic field transition that's then sensed by this this magnetic sensor to detect the position of the feed roller. So this is the laser assembly. We've got a laser diode here. Beam comes out here, bounces off there, and onto this little mirror. And there's a couple of little magnets on the back, so these coils produce the XY scanning across the plate. And this is the actual laser diode, a tiny little laser diode, which is red. I'm guessing it's probably 633 nanometers, and that was mounted in this sort of tube with 3 tiny little alignment screws in 2 positions, so you can actually adjust the position by adjusting the screws. I'm not sure what power this is. Also, I don't know what current it was meant to run at, but doubt it's hugely powerful. There's no obvious sign of any heat sinking, and doesn't also appear to be any optical feedback either, as far as I can tell, unless that's elsewhere in the system. So it's probably run at fairly low power. So removing this plate with this is an aluminium plate with the lenses glued on. I'd imagine these are fixed in some sort of jig and then glued in place. There's the mirror there that reflects the laser down onto the plate. It looks like it might have some sort of dichroic coating on it as well. And this looks interesting. So this is the photomultiplier tube, and it seems to have this sort of fibre pigtail to transfer the light from the plate down to the actual sensitive area of the photodiode. Obviously the laser is providing the raster scanning, so this doesn't need to be an image sensor or a line image sensor. It just needs to look at the instantaneous light level as the laser scans across the plate. And this is the actual photomultiplier. It's quite a tight, cute little photomultiplier tube made by Hamamatsu, of course, who seem to make pretty much all the photomultipliers. And usually it's actually soldered into the PCB rather than socketed. And you've got the resistive divider chain here, and a bit of filtering capacitance, then the output connector via this little miniature coax that goes up to the processor board. And this is the fibre optic assembly. So this takes the line of fibres here and concentrates it down to the photomultiplier. If we shine light through, you can see there's also a blue filter on here, so that's obviously selecting the specific wavelength that the phosphor-plate emits when it's excited by the red laser. And of course there's no need for these fibres to sort of map exactly, because it's the laser scanning that produces the spatial information. So all it needs to make sure is that light from anywhere on here does actually come out somewhere. It's also not super accurate that the optical path lengths are equal or anything, because it can just calibrate out the differences. It can just do a scan with like a calibration target or something to map any differences in the optical attenuation. Whether it does that in the unit or whether there's some sort of external calibration unit, I don't know. I've just taken that filter off, and you can see that obviously there's an approximate top to bottom relationship between the light going in and coming out, but the actual pattern is fairly arbitrary. And we'll take the next layer off the optical assembly. We've got the motor drive, so you can see we've got stepper motor here, belt drive down to here, then a worm gear onto the actual roller. I think we've probably got some sensing of the position going on here. The other thing we've got here is a row of LEDs. Now this will be for erasing the image from the plate once it's been scanned. So let's see what wavelength they use for that. And these are very bright red LEDs. Interestingly, it looks like there's actually 2 dye in each package, which I've not seen before. There's actually 2 dye in each LED, which is a bit unusual. And looking closer at this, it looks like the plate is actually carried on this belt, sort of grey, sort of rubbery type belt material. And there's also these sort of black brushes, which obviously to keep the light out, because obviously that photo multiplier is very sensitive, so you need to keep all the extraneous light out of the sensing area. And so it's driven from that end, and then the encoder is on the other end, so that any slop in the belt is compensated for. So it's using the actual output from the encoder to time the scanning. And the belt runs over these sort of cylinders, which have got nice bore races. Though again, this is super high quality mechanics. And there's this board inside, which I'm assuming is some sort of sensor. Yeah, there's some photo detectors here that go through these sort of tiny little slots. So I imagine that's detecting the plate as it goes through. It might also, actually, these may come think of it, these might also be detecting the endpoints of the laser scan, so it can actually detect the laser, so it knows the start and end points of the scan to compensate for any optical distortions or timing things. So yeah, in fact, looking at that, I think, because these have got very small slots on there, as the beam scans across here, it'll also see a pulse at the beginning, at the end of the scan, so it knows exactly when that starts and stops, and it can adjust its timing to get the scaling on that direction correct. So actually a slightly surprisingly complicated bit of a kit. Incidentally, this is the laser scanning mirror, so it's just a mirror with two little magnets glued to the edge on a sort of springy mount, and that's the belt that the plate gets pulled along by. But I think that's probably about the smallest photo multiplier I've seen. Certainly you don't expect to find photo multipliers in gear this small. What, I thought was just a simple optical scanner actually turned out to be something a little bit more complicated. I don't know whether these phosphor-plate things are really still in use. You see a lot of direct digital X-ray stuff around now, so I don't know whether this tech is really still used for dental, or whether it's all gone completely digital these days. Maybe if someone actually knows, you can leave something in the comments. But it's so it's quite an interesting tech, a sort of stopgap between the old film and developing and fully digital X-ray processing.